Failing the Master Electrician Exam by a single point indicates that your performance was very close, suggesting that targeted improvements in specific areas can lead to success. Your mastery of code-related questions demonstrates a strong foundation and a thorough understanding of the National Electrical Code, or NEC. However, to improve, focus on several key areas. Firstly, you need to prioritize memorizing NEC tables and numerical data. This is crucial for answering closed book questions effectively. Make sure you review the tables thoroughly and commit key information to memory. Secondly, enhance your understanding of motor and transformer theory. Concentrate on grasping and applying motor and transformer principles to tackle theoretical questions effectively. Thirdly, develop a strategy for tackling closed book questions. Practice estimating answers or using logical deduction for questions that rely on memorized information. Now, let's outline a structured study plan for your retake. Number 1. Systematically review NEC tables and numerical data. Utilize a study guide or online resources to memorize important values and calculations. Number 2. Dedicate time to studying motor and transformer theory. Consult textbooks or online resources to enhance your understanding of motor and transformer principles. Number 3. Engage in practice sessions focused on closed book questions. Simulate the closed book section of the exam by practicing questions without any references. Number 4. Consider incorporating additional study materials into your preparation. Explore other exam prep books or online courses that may cover the areas where you face challenges. Beyond these specific areas, keep in mind time management and code familiarity. When it comes to time management, use a timer to practice answering questions within the allotted time frame. This will help you pace yourself during the actual exam. As for code familiarity, familiarize yourself thoroughly with the specific code issue for the Minnesota exam, which may differ from other jurisdictions. Finally, strategically use the waiting period. Take advantage of the 6-month waiting period to focus on studying and improving your knowledge base. Now let's talk about power factor. Power factor is the ratio of real power flowing to the load to the apparent power in the circuit. It can range from 0 to 1, and it is commonly expressed as a percentage. Circuits with resistive loads, such as heaters or incandescent lights, have a power factor of nearly 1. Circuits with inductive loads, such as motors and transformers, have a power factor less than 1. This means that the current is lagging behind the voltage. Low power factor can cause several problems, including increased energy costs, voltage drops, and equipment overheating. To increase the power factor on a circuit with inductive motors, you can use capacitors. Capacitors store electrical energy and can release it back into the circuit when needed. When connected to a circuit with an inductive load, a capacitor provides leading reactive current, which offsets the lagging reactive current drawn by the inductive load. This brings the power factor closer to 1, improving the efficiency of the electrical system. The size of the capacitor needed depends on the size of the motor and the amount of power factor correction required. Consult with a qualified electrician to determine the appropriate size capacitor for your application. Squirt cage motors are induction motors commonly used in industrial applications. The speed of a squirt cage motor is determined by the frequency of the power supply and the number of poles in the motor. The formula for calculating the synchronous speed of an induction motor is synchronous speed equals 120 times frequency divided by the number of poles. The actual speed of the motor is slightly less than the synchronous speed due to slip. Slip is the difference between the synchronous speed and the rotor speed, and it is typically expressed as a percentage. A transformer is a device that transfers electrical energy from one circuit to another through electromagnetic induction. It typically consists of 2 or more coils of wire wound around a common core. The primary coil is connected to the input voltage, and the secondary coil is connected to the output voltage. The ratio of the number of turns in the primary coil to the number of turns in the secondary coil determines the voltage transformation ratio. Transformers can be used to step up or step down voltage levels. Step-up transformers have more turns in the secondary coil than in the primary coil, while step-down transformers have fewer turns in the secondary coil than in the primary coil. The open book portion primarily tests your ability to navigate the NEC and applies provisions to specific scenarios. It assesses your understanding of code requirements and your ability to locate relevant information efficiently. The closed book portion tests your knowledge of fundamental electrical concepts, code requirements, and industry best practices. It evaluates your ability to recall and apply this knowledge without the aid of reference materials. Master Electrician exams often include questions on a variety of topics, including general electrical knowledge, circuit calculations, wiring methods, equipment installation, and safety requirements. Questions may cover topics such as Ohm's law, Kirchhoff's laws, series and parallel circuits, voltage drop calculations, conductor sizing, overcurrent protection, grounding, bonding, and equipment selection. Being familiar with these topics is essential for success. Knowing the definitions of common electrical terms and understanding basic electrical principles are fundamental to success in the exam. Familiarize yourself with terms such as voltage, current, resistance, power, impedance, reactance, inductance, capacitance, and power factor. Additionally, understanding basic electrical principles, such as Ohm's law and Kirchhoff's laws, is essential for solving circuit-related problems. The NEC contains numerous tables that provide essential information for electrical installations. These tables cover topics such as conductor ampacity, conduit fill, box fill, voltage drop, and equipment grounding. Memorizing key values from these tables and understanding how to use them is crucial for answering code-related questions accurately. The exam may include questions related to motor circuits, including motor overload protection, short circuit protection, and control circuit wiring. Be familiar with the requirements for sizing motor branch circuit conductors, selecting overcurrent protection devices, and installing motor control equipment. Additionally, the exam may cover transformer installations, including transformer overcurrent protection, grounding, and ventilation. Be familiar with the requirements for sizing transformer primary and secondary conductors, selecting overcurrent protection devices, and ensuring proper ventilation for transformers. The NEC specifies different wiring methods for various applications, including rigid metal conduit, intermediate metal conduit, electrical metallic tubing, flexible metal conduit, and non-metallic conduit. Be familiar with the requirements for installing these wiring methods, including support spacing, bending radii, and conductor fill limitations. Understanding proper grounding and bonding techniques is essential for ensuring electrical safety. Be familiar with the requirements for grounding electrode systems, equipment grounding conductors, and bonding jumpers. Additionally, understand the purpose of grounding and bonding and how they help to prevent electrical shock hazards. The exam may include questions related to electrical safety, including lockout/tagout procedures, personal protective equipment, and arc flash hazards. Be familiar with the requirements for working safely around electrical equipment and how to protect yourself from electrical hazards. Effective time management is essential for completing the exam within the allotted time. Pace yourself and allocate your time wisely to ensure that you have enough time to answer all of the questions. If you get stuck on a question, move on and come back to it later. Be sure to review your answers before submitting the exam to catch any errors or omissions. There are many resources available to help you prepare for the Master Electrician Exam. Consider enrolling in a review course, purchasing study guides, or using online practice exams. Utilize these resources to reinforce your knowledge and identify areas where you need additional study. Here are some more specific topics. Conductor ampacity refers to the maximum current, in amps, that a conductor can carry continuously under specified conditions of use without exceeding its temperature rating. The ampacity of a conductor is determined by several factors, including the conductor material, size, insulation type, and installation method. The NEC provides tables that list the ampacity of various conductors based on these factors. Conduit fill refers to the percentage of the cross-sectional area of a conduit that is occupied by conductors. The NEC limits the amount of conduit fill to prevent overheating of conductors and to ensure that conductors can be easily pulled into and out of the conduit. The allowable conduit fill depends on the type of conduit, the size of the conduit, and the number and size of the conductors. Box fill refers to the maximum number of conductors, devices, and equipment that can be installed in an electrical box. The NEC specifies box fill requirements to prevent overcrowding of boxes and to ensure that connections can be made safely. The allowable box fill depends on the size of the box, the size of the conductors, and the type and number of devices and equipment. Voltage drop refers to the decrease in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction and can reduce the efficiency of electrical systems. The NEC recommends limiting voltage drop to a maximum of 3% for branch circuits and 5% for feeders. Equipment grounding ensures that non-current carrying metal parts of electrical equipment are connected to ground. This provides a lower impedance path for fault current to flow back to the source, which helps to trip over current protection devices and prevent electrical shock hazards. The NEC specifies requirements for equipment grounding conductors and grounding electrodes. Motor overload protection protects motors from overheating due to excessive current. Overload protection devices, such as thermal overloads and fuses, are designed to trip and disconnect the motor from the power supply when the current exceeds the motor's full load current rating. The NEC specifies requirements for motor overload protection based on the motor's horsepower, voltage, and type of enclosure. Short circuit protection protects electrical systems from damage caused by short circuits. Short circuit protection devices, such as circuit breakers and fuses, are designed to trip and disconnect the circuit from the power supply when a short circuit occurs. The NEC specifies requirements for short circuit protection based on the circuit's voltage, current rating, and available fault current. Control circuit wiring refers to the wiring used to control motors and other electrical equipment. Control circuits typically operate at low voltage and are used to start, stop, and control the speed of motors. The NEC specifies requirements for control circuit wiring, including conductor size, overcurrent protection, and wiring methods. Transformer overcurrent protection protects transformers from damage caused by overloads and short circuits. Overcurrent protection devices, such as circuit breakers and fuses, are installed on the primary and secondary sides of the transformer to protect it from excessive current. The NEC specifies requirements for transformer overcurrent protection based on the transformer's kilovolt-ampere rating, voltage, and impedance. Transformer grounding ensures that the transformer's neutral point is connected to ground. This provides a low impedance path for fault current to flow back to the source, which helps to trip over current protection devices and prevent electrical shock hazards. The NEC specifies requirements for transformer grounding based on the transformer's voltage and winding configuration. Transformer ventilation ensures that transformers are properly cooled to prevent overheating. Transformers generate heat during operation, and excessive heat can damage the transformer's insulation and reduce its lifespan. The NEC specifies requirements for transformer ventilation, including minimum clearances around the transformer and the use of fans or other cooling devices. Rigid metal conduit, or RMC, is a type of steel conduit that is used for electrical wiring. RMC is the heaviest and thickest type of conduit and is suitable for use in harsh environments. The NEC specifies requirements for the installation of RMC, including support spacing, bending radii, and conductor fill limitations. Intermediate metal conduit, or IMC, is a type of steel conduit that is lighter and thinner than RMC. IMC is suitable for use in many of the same applications as RMC but is less expensive. The NEC specifies requirements for the installation of IMC, including support spacing, bending radii, and conductor fill limitations. Electrical metallic tubing, or EMT, is a type of steel conduit that is lightweight and easy to install. ENT is suitable for use in dry locations where it is not subject to physical damage. The NEC specifies requirements for the installation of ENT, including support spacing, bending radii, and conductor fill limitations. Flexible metal conduit, or FMC, is a type of flexible conduit that is used for connecting electrical equipment. FNC is suitable for use in locations where flexibility is required, such as connecting motors or lighting fixtures. The NEC specifies requirements for the installation of FMC, including support spacing, bending radii, and conductor fill limitations. Non-metallic conduit is a type of conduit made from plastic materials such as polyvinyl chloride or PVC. Non-metallic conduit is lightweight and corrosion resistant and is suitable for use in wet locations. The NEC specifies requirements for the installation of non-metallic conduit, including support spacing, bending radii, and conductor fill limitations. Grounding electrode systems provide a connection to the earth for electrical systems. The grounding electrode system typically consists of one or more grounding electrodes, such as ground rods, ground plates, or metal water pipes. The NEC specifies requirements for grounding electrode systems, including the type and size of grounding electrodes and the methods for connecting them to the electrical system. Equipment grounding conductors, or EGs, provide a path for fault current to flow back to the source in the event of a ground fault. EGC are typically made of copper or aluminum and are sized according to the requirements of the NEC. The NEC specifies requirements for EGC, including the size, type, and installation methods. Bonding jumpers are used to connect metal parts of electrical equipment together to create a low impedance path for fault current to flow. Bonding jumpers are typically made of copper or aluminum and are sized according to the requirements of the NEC. The NEC specifies requirements for bonding jumpers, including the size, type, and installation methods. Lockout/tagout procedures are used to prevent accidental energization of electrical equipment during maintenance or repair. Lockout involves placing a lock on the disconnecting means to prevent it from being turned on, while tagout involves placing a tag on the disconnecting means to warn others that the equipment is being worked on. The NEC requires that lockout/tagout procedures be followed whenever electrical equipment is being worked on. Personal protective equipment, or PPE, is used to protect workers from electrical hazards. PPE includes items such as rubber gloves, safety glasses, and arc-rated clothing. The NEC requires that workers wear appropriate PPE when working on or near energized electrical equipment. Arc flash hazards are a serious electrical safety hazard that can cause severe burns and other injuries. Arc flashes occur when electrical current flows through the air between two conductors. The NEC requires that employers conduct arc flash hazard assessments and provide employees with appropriate training and PPE to protect them from arc flash hazards. Review Ohm's law, which states that voltage equals current times resistance. This fundamental law is the basis for many electrical calculations. Understand series and parallel circuits. Know how to calculate voltage, current, and resistance in series and parallel circuits. Understand how to calculate voltage drop in conductors. Be familiar with the NEC tables for conductor ampacity and voltage drop. Master conductor sizing for various applications. Be able to select the appropriate conductor size based on the load, voltage drop, and other factors. Understand overcurrent protection and be able to select the appropriate overcurrent protection device for a given circuit. Know the different types of wiring methods and their applications. Understand the requirements for grounding and bonding. Be familiar with the NEC requirements for electrical safety. Now for some additional advice. When answering multiple choice questions, read each question carefully and eliminate any answers that you know are incorrect. If you are unsure of the correct answer, try to make an educated guess based on your knowledge of the subject matter. If you are unsure of the correct answer, mark the question and come back to it later. This will allow you to focus on the questions that you know and avoid wasting time on difficult questions.